First of all, I think you guys understand you are allowed to have one more week to finish the programming assignment number 2. All right, and the original due date is set to tomorrow. That says you still have one more week. All right, so about the submission of your programming assignment, any question or any possible comment on this? If no, so right now, let us get back to the discussion on chapter 6. All right, so that's we let you know if we want to have the possible calculation. You can use the X per feet software provided by this taskforce. I think you guys can check it, and you can download the X per feet to have the calculation or the plot for some of the figures. And right now, let me continue to check shifty and truncated distributions. Okay, so why we need to have a shifty and truncated distribution? Wait a moment. Sometimes even we have the standard distribution, but it doesn't fit the needs of our application. So it's possible to modify a distribution and so that you have the better fit in some cases. And taking the example, bank teller, all right, it says if you want to speed up the processing time of the teller in a bank, here we have a possible limitation. It says bank teller cannot serve a customer in less than 30 minutes. So that says it is impossible to have the time less than 30 seconds. If you employ a distribution, a standard distribution with the value lower than 30 seconds, then it cannot fit the requirement of the application or the case. So all you can do is shift distribution to the right, and so that this allow value less than 30 seconds. Well, for this reason, or for some of the similar reasons, we need to have the shift operation. And the next one, actually, it is called the truncated distribution. It says even you shift it, but it doesn't mean less than, perhaps not larger than. So put them together, then you have another version, truncated distribution. All right, so even we have the standard distribution, we're still allowed to have the two operations, and so that you can have the better fit for your case. Okay, so if we talk about shifted distributions, it says normally we should have these. Standard distribution have the range of 0 to infinity. For example, you can look at exponential, gamma, variable, log normal, PD5, PD6, and log logistic. Because of these, so you need to shift. Like the previous example, for example, you can set gamma to 30 seconds, right? All right, so if you want to do so, then you need to apply the operation of shift. Okay, If you want to apply the operation of shift to the right. If we have these, given these, the standard distribution, and it says if you want to have the new distribution, how to do? You use this. So you can use this way. F of x represent. Wait a moment. So you can use this, the original PDF. The original PDF. And right now, this is a new version of the PDF if you want to have the shifty version. All right. So I think this one it's really easy, but at this we need to remind you of this shifty version. Okay, so this is a shifty version if you want to have the new version. And another one, it is called the truncated version because it is not possible to have the range. Okay, so we want to change the range. For example, we want to change the range to A to B. All right, A to B, and then you need to have the truncated version. If you have the truncated version, how to do? Likewise, if here we have f of x, if you want to have a truncated version, so that you have the range from A to B. From A to B, and then how to have the new version. This time, the new version. Actually, this new version, we can have a new function, f prime of f of x. The same, this one, you have f prime of x, but you need to have these. Okay, so look at this normalization. If you want to have the new version, you need to apply normalization. Right now, if you have the new range from A to B, it's a subset of the interval from 0 to infinity. If you want to do so, you need to apply normalization. So how to do? F of s over the integral from A to B. All right. Why? Think about this. If you have the current range, then you cannot have the total probability of 1. If you want to have a total probability of 1 for the new function f prime of x, normalization can achieve this. So that's why we need to employ normalization to get the new PDF f prime of x. All right, so I think the two operations corresponding to the two new versions. Version 1, shifted version. Version 2, this is the truncated version. All right, so provide you the two versions if you want to have some cases like the two versions. All right, that's it. So truncated version and shifted version. About this, any question? If no, in the following, I may skip the Bezier distributions and also skip the specifying multivariate distribution, correlation, and stochastic process. All right, and I go through quickly, and then we jump to discuss selecting a distribution in the absence of data. Let's say skip these and skip these and jump to these and the remaining. And of course, for the remaining, some of them may be skipped. Okay, so this one, I think you guys can check some of the description. I think let me totally skip this part. And also this part. All right, so let me discuss the current one. If you want to have the distribution, but you don't have any data, that says in the absence of data, then how to do? Look at this. Sometimes it is not possible to have the data, right? Okay, so if you have this way, then what is a possible distribution? All right, so in the following, we want to have these because no data, so of course, we don't have any information to have the proper selection. Even no proper selection, but we try to have the possible suggestion. Right now, no data, right? No data, then you need to have the selection based on some limited information. Actually, not no information, but no detailed data. Okay, if you don't have the detailed data, for example, you simply have minimum and maximum, only the limited information, then what is a possible distribution? I think you guys have the suggestion here, uniform distribution. Why uniform distribution? Because uniform perhaps it is the simplest one, right? And right now you just have the information from minimum value to maximum value. So no choice. Possibly you can apply uniform. Okay, so this is the first one. And the second one, minimum, max, and the mode. Something like this. Minimum, maximum, and mode. So mode here. So it says no other choice. It is the mode. So you can apply triangular. And also, this one I think not really easy to check. But at least if you have a minimum, maximum, and mode, and also mean, the authors that you know, possibly you can use beta. Okay, so about this, maybe not really easy to illustrate why we choose beta to be the suggested distribution. But I think you can have you can direct. I mean, just accept. Actually, it is a suggestion. Even not really easy to understand why we should use this suggestion. But this is a suggestion for you. All right, so that says if you don't have any data, it doesn't mean any data. The limited data, you can have the suggestion, uniform, triangular, and beta for the three cases. Okay. All right, so I think, of course, the task for that you have some more details, but I think just these, you can apply these rules to have the suggestion. Okay, so this is the way to specify distribution in the absence of data. And actually, the task that you have some possible comparison. Okay, so given some example, and of course, you can have some way to have triangular and beta. And also, correct distribution should be normal, right? And it says if we have the log normal, okay, sorry, log normal here, and is it possible to have a triangular to have the fitted version? Sure, you can have this one, perhaps the best fit. All right, so it says if you don't have any, you don't have any idea, then using triangle perhaps okay. And how about beta? Still okay, but not really okay for the current case. All right, so you can have the distribution. All right, and of course, you can try to check the error. How about this? The original one, no problem. And how about this? Previously, this is the one. Oh, wait a moment. It says this one. Okay, sorry, let me have the correction. It doesn't mean the best fit is this one. Sorry, let me have the correction. And how about this beta? It says beta is the best one. All right, so it doesn't mean we have the direct image and then to have the result. Let me get back to this. It says must carry out the sensitivity analysis, but we do not check these. So I don't think right now you have any analysis like sensitivity analysis that you have the beta solution. At least I just want to let you know, if we don't have any information, then we can apply triangular, we can apply beta. Here, it try to convince you beta perhaps that you have the best fit. This one. Okay, so even you can have the almost better fit using triangular. It says beta perhaps can even better for the Philly version. All right, so I do not ask you to pursue the best one, but just want to let you know we can have these suggestions. Okay, if you want to have the comparison and so that you have the best choice, you can do some comparison. For example, you can use sensitivity analysis. Unfortunately, we do not touch sensitivity analysis, so this one we cannot let you know why. Finally, we choose beta. But if we have more information, of course, beta will be the best one for you. All right, so this is the selection if you don't have actually you don't have enough data. You just have the limited data. You can have the previous suggestion, uniform, triangular, and beta. And that's all. So this is the selection of a distribution if you don't have enough data. And finally, data check this one, models of arrival process. Normally from chapter 1, normally we have a person. Okay. And it says person most commonly used model. Okay. So the first choice, person. If we have a person and want to have the beta fit the arrival using person process, and then look at this. Customers arrive one at a time. No batch. Okay, no batch arrival. So this is the first one. And the arrival time instance does not depend on the number of arrivals in the early time interval. That says irrelevant to these. And also does not depend on time of day. All right. So arrive one at a time. That says no batch arrivals, and also follow some independence property. If you have some of the properties like these, and then possibly you can apply Poisson process. But sometimes we don't want to use the pure or simple Poisson process. Okay, and it says you need to have a batch. All right, so if you want to have a batch arrival, you need to specify batch arrival. So another distribution is necessary. All right, so you still can apply Poisson, but you need to have the actual distribution to describe the batch arrivals. And also, if you have the Poisson process, but you have the non-stationary. Non-stationary says not the same rate. Okay, not the same rate as time goes. So you look at these. Arrival rate now allowed to be a function of time. All right, so it says for Poisson process, you can have the discretion, the actual distribution for the batch arrivals. And also you can allow the rate to be different. And so that you have the non-stationary Poisson process. How to do? Look at these. The interval, you have a rate 1 and another rates. If you have the specified rates, you just follow the time duration and follow the rate to have the individual Poisson, right? And if we have the continuous function, then you can have the approximation using the current, something like you have the step size function. All right. So you can have the step size function, then you can have the approximation if you have the continuous arrival rate. All right, so this one, talking about the non-stationary Poisson process. If you have the continuous one, you can use the current version to have the proper approximation. All right, that's it. So from chapter 1, we know Poisson only. And can we have any further version based on Poisson? Yes, we can have the batch Poisson. And also, we can have the non-stationary Poisson if we can specify the rates properly. If you can do so, you still can have the extended two versions, batch Poisson and non-stationary Poisson. And that's all. So possibly you may modify Poisson process to have the two new versions. Okay, so about the two new versions, okay for you? I think no problem, so let me continue. And finally, this is the assessing the homogeneity of different data sets. Okay, about this, I think I do not check it further. Okay, so this one, the same, I skip it. So it says, I skip this one. And also skip the 2. All right, the 2s. And so that the 3 items here, I totally skipped, right? So you can have your own way to check it, or you don't want to check it. And the 2 parts will not be contained in the final exam, so don't worry. Why I skip them? Because we seldom use them, so that's why I don't want to go through the 3 parts of this chapter. Okay, so these are the discussion for chapter 6. Up to now, any questions? All right, maybe let me have check by nominating some of you. All right, so Haoen, any question up to now? And one more. Youjun, any question? No response, so let me continue. Daron, any question? Okay, so I think based on the 2 feedbacks, I think we can continue, and it's up to you. And also, I will that you have the reference exercise, including the exercise of chapter 6 soon, so you can try to check it. And of course, no need to hand in, just the reference exercise. Well, for our final exam, of course, I will postpone because right now, using 16 weeks to finish the discussion, perhaps it is impossible. So I will postpone the final exam and also the final oral presentation. But at least I just want to let you know, if we want to have the final exam, we will cover the chapters we reach to chapter 8. Okay, if I mention specifically the chapters, we should have chapter 1, 2, 3, 4, and then 6, finally to 8. All right. If you guys ask me to write it down, final exam, including chapters 1 to 4, then 6 and 8, including supplement. Okay, so one more chapter we need to go through, and finally we finish the range for the final exam. And of course, later I will check when will be the appropriate day to have the final exam. All right, so I will check it, but I will definitely have maybe 1 week before the exam. So after checking, I can let you know quickly. But right now, let us go through chapter 8. Go through chapter 8 first. So chapter 8, right now, we want to consider how to generate random variables. That says random variables. We emphasize generation. Okay, so how to have the way to generate. All right, so we will have the short introduction and then let you know how to generate. before how to generate, of course, we already have the general approaches. And then we check how to generate continuous random variables, discrete random variables, and also try to check some. Actually, this one, I did not go through, so this one, we will skip it. And also, we want to check how to generate arrival process. If not Poisson simply, we may have the others. For example, the non-stationary Poisson and batch Poisson. All right, so in this chapter, we will go through these. So about this, it says, using the analogy in chapter 6, we assume a distribution has been specified already, right? If specified already, then we want to know how to generate, right? So how to generate random variables? In fact, in chapter 1, think about how to generate the selected Poisson, right? Something like if no one tell you how to generate Poisson, but at least you are asked to generate Poisson, then how to do? Well, maybe you have a question. In chapter 1, you don't know how to do. But this chapter, that you know the reason why. If we generate Poisson, we use that way to generate Poisson. In fact, not directly generate Poisson, but generate Poisson by checking the inter-arrival time. Inter-arrival time. Okay, because inter-arrival time for Poisson is exponential, so we can check using exponential to know when we will have the next arrival for Poisson. But think about this. In chapter 1, to generate Poisson, we use the IID uniform U of 0 to 1, right? So this is the basic one. So basic ingredient, this one. Normally we need to have the ID U0 to 1 random variables, right? So this is a basic ingredient. Well, basic ingredient perhaps one or more U, right? With one or more U, and then we need to have the black box. Okay, the black box, here we call transformation. Okay, so we can transform these to the random variables. And the random variables follow the desired distribution. Is it possible? Of course, it's possible. So that's why we have the black box and call the black box the transformation. You see, all algorithms should have the same general form. Through the transformation, possibly you can have the random variable. Okay, so we want to do this. And in fact, the basic gradient coming from the good random number generator, we use it already in chapter 7. And actually, we don't go through chapter 7 because the following reason: no time to go through that one, and also even we go through that one, perhaps we only have the final conclusion. We use it simply, so that's why finally I do not go through chapter 7 and jump to chapter 8 directly. Right now we have the discussion, right? Okay, so from that page, the previous page, we should have the possible black box to have the transformation. If we have the transformation, we will consider the following. Of course, is it exact? If possible, of course, we should have the exact approach. And also, is it efficient? So check efficiency. And how complicated the algorithm is. So we check the complexity. And also, is it robust? So we check robustness. But it doesn't mean we'll always check these, but sometimes we may check some of the factors here. Okay, so you see, checking exact, not appropriate. It says we may have this one to generate some of the random variable. But if you only use a central limit theorem, you just have the approximate version. Okay, so sometimes you have the desired version through some of the specified formula. For example, the formula here. As for why this formula, in fact, not really difficult. Later we will let you know the reason by checking the philosophy of the transformation. And if we have this version, think about this. How about the storage? Low storage. How about the speed? Really fast. Okay. And how about the parameters? And here it says maybe not really clear. So it says maybe regardless of parameter value, then we have the efficient. Okay, about this, not really clear, but at least you will know if you have the formula. Storage is not so high, so we have a low storage, and the speed still okay. So about the formula, understandable, and can be implemented, right? And only use one U. Really? At this moment, maybe not true. So at this, you have multiple U. All right. If you have one U, sure, the best one, but sometimes not a single U. So possibly you may have multiple U. So it doesn't mean you can fit all the factors, but you can fit some of the previous factors. Okay, so up to now, we just let you know we can have the black box. Apply the black box, then you can have the transformation. So we want to know what is the black box. And if you know the black box, you just follow that black box to help you to have the generation of random variables. Okay. And right now, let us let you know. Normally, we may have the following general approaches to generating a univariate random variable. Uni means a single variable. Okay, so inverse transform, composition, convolution, acceptance, rejection, and special properties. Okay, so you may have these. Okay, wait a moment. Let me turn off Siri. All right, so let us check the first general approach, inverse transform. Of course, we can specify these random variables x. And if x has a distribution, CDF, okay, CDF F. Okay, and right now, CDF, of course, we can think it is a continuous and increasing, right? If we want to have the generation by given F, So what is the way to have the generation? Allow you have the U. Okay, U value taken from uniform. Okay, follows. Okay, so the tilde here, it follows. Follows the distribution U from 0 to 1 to get one value U. Get one value U, and then you can use the inverse function. This inverse function, so that we have the inverse transform. So inverse function to have the proper transformation, so that you can have the random variable. Well, this is the way. Is it true? First of all, we can use a way to have the way to understand why inverse transform method. Okay, it says you can have the value here for in between 0 and 1, right? So it says you can have a random value U. You try to have the mapping. If you want to have a mapping, what is the way to have the mapping? It says inverse transform, right? So we need to find the inverse transform. So the inverse transform allow you to find the corresponding x. That's it. If you have another value, you may have another x. So using the current way seems to be true, but we still don't have the formal proof to check it. The formal proof to check it, is it true? So it says we have the way if lower than or equal to x sub 0, right? And right now we apply the function f for both sides. Still keep the inequality, right? If you keep it, and then this one is u, and also fall within this. And know that u in between 0, but right now lower than the specified value f of x sub 0. So uniform u. So use the two sides to have the difference, so that you have the probability. With the probability, then we have this. If we have this is a CDF. Perhaps you can treat it unknown. Treat it unknown. Finally, if you have this, you will find CDF of x is f here, right? So it says this one confirmed. Given the f, using the current way, random variable x still follow, and actually not still, actually follows the CDF of f, and that's it. And next one, we can check by using a picture. Okay, so previously we checked it already, but it says if you want to have u1 x lower than this, so you need to specify a value, this one, u1 lower than some specified value. So it says if you have this property, then you can have this. I think this one, by using the figures, and you can have the relationship. The relationship still that you have the CDF of x follows function f. And that's all. So right now it says if we have the inverse transform, we need to invert f, so that you have this, right? Invert f, and so that you have f inverse. How that means? In the following, let us have some examples so that you can understand the meaning for this. So up to now, let me get back to this one. We try to emphasize this. That's all. So remember, U And remember F inverse. To find F inverse, how to do? Right now, let us have some examples. If we have the well-bound distribution, this one, and well-bound distribution that we have a CDF here. So CDF here, how to find inverse one? It's really easy. Someone like you have a figure and try to give a U, and you try to find this X. Okay, so find X. Right? So let us have the equality. U equal to the CDF and try to find X. If you want to find this X, and then you have the second equation, right? And also you have this one by taking logarithm, right? Well, finally, it's really easy. You should have this. Right? Okay, once you have this, what that means, this is the results, but this is the inverse function. So should we have the inverse function explicitly? No, it's really easy. Given U, try to find X. Once you find X, and then use the formula to generate X, and then that's done. So this is the first example. Any question? So let me stop here and try to nominate some of you to let me have your feedback, understand this. Then you have 2 minutes to check this. And after 2 minutes, we'll take a break first. And then, since next class, 5 minutes later, I will ask you guys understand this or not. Okay, so right now, look at this for 2 minutes. And this is the inverse transform algorithm for the well-bound distribution. And you know, well-bound distribution, later we can rethink about exponential. But look at this example first. If you understand or not understand, later we can re-examine this example. So you guys check it for two minutes. 2 minutes later, we will have a 5-minute break. And since next class, we will have the re-examination on this example. Okay, by this, I ask you guys to check this example in detail. Before we take a break, I forgot to let you know this. Here we have 1 minus u, but we there 1 minus u to be a simple u. So to be a simple u, we use u directly. The u here and the u here, they are not the same, but we treat 1 minus u to be u prime. To be u prime still follow the value from a u. So that's why we can generate one value from u. And substitute the value into the function directly to replace 1 minus u. So that's why step 2, we have a beta multiply minus log u simply. Okay, so previously I forgot to let you know the reason. And this is the explanation on the place here to let you know why we have the new version u, not 1 minus u. And sometimes you can apply the similar reason or the same reason to the other cases. It's still valid. So this is the way to use u rather than 1 minus u. If you don't like it, you want to use 1 minus u, still okay, but u will be simpler. So that's why we use the new version u rather than 1 minus u. Okay, so I think let us take a break. After 10 minutes, and then we re-examine this example. All right, take a rest.